This question. An object M, mass equals 15 kg, is dropped from an altitude of h equals 6.38 times 10 to the power of 6 meter above the Earth's surface. The height is actually equals to the Earth's radius. Ignoring air resistance, what will be the velocity of M when it falls to the surface of the Earth? Okay, I just had one more air here. Okay, so basically you just drop something. If this question is drop near the Earth's surface, it would be very easy. You can just simply use kinematics like free fall, right? You don't have to do anything to do with something to do with energy. Okay, yeah, if it's near to the Earth's surface, it's easy. But now, it's also easy, but you have to think differently. So that's Earth's surface. This is going to be the radius, RE. An object is actually starting to fall at here and finally fall to the surface. So basically the question asking for the velocity right here. So obviously the initial velocity equals 0, and then this is the h, and then this is going to be the initial distance between the Earth and the M, right? And then because this is the final position, right? So this is actually RE is actually equals the final distance between the Earth and the M. Okay, now think about in this process from here, initial position to the final position. There's no any non-conservative force acting on them. It's only gravity acting on it. So we can definitely use the version 3 of the work energy theorem. So that means delta KE plus delta GPE equals 0. Okay, and then we just need to, of course, this one can also written as KE initial plus GPE initial equals KE final plus GPE final. Basically, the mechanical energy added together at the initial position equals the total mechanical energy to the final position. So you can tell from the initial position we don't have the kinetic energy, so this is gone. And then at the final position, do we have the gravitational potential energy? Be careful, we do. Okay, so right now, so we now it depends where you set up your reference, right? So if we set the reference set at infinity, and then we do. Okay, so and then the GP initial is going to be negative big G, that's a constant, M, that's the mass of the Earth, times M divided by RI. Now be careful, we do not have the square, otherwise that's going to be the force, and also negative. Okay, now only when the reference set at infinity, so we have this formula for the gravitational potential energy. And then that's GPE initial. The KE final is 1/2 mv final squared, and then GPE final. So be careful, it's not 0, it's negative G M E M R final. Okay, not actually, we don't need to know that, that's extra information. Yeah, put them together. Okay, and then solve the v final here. So we can actually, because move this over the other side, it become positive. Then we can factor the g and me because they're the same. So we can get g m, and inside we should get 1 over rf minus 1 over ri. Okay, and then 2 multiply 2, and eventually take square root. So this is going to be the v final. Okay, so then we just plug in everything and do a calculation. Okay, we plug in 2 times 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24. That's the mass. And then 1 minus the r final is actually the Earth's radius. I forgot to put an e here. 6.38 times 10 to the 6. Subtract. The initial distance is actually 2 times of the radius. So 2 times 6.38 times 10 to the 6. Okay, so that's the final, of course. So there are a lot of different ways to do this. I would actually do this first, and it actually becomes 1 over 2 times this, and let's cancel with this 2. But anyway, I leave this to you to calculate. So eventually, so I just give you the answer. So the answer should be 7.89 times 10 to the power of 3 meter per second. I calculated just once. I'm not sure if I did right, but that should not be a problem. So just quickly summary. So for this kind of question, don't forget, you can still apply the work energy theorem. So in this case, because there's no non-conservative force doing any work, because we ignore the air resistance, so this one, it becomes a version 3. Version 3 is actually conservation of mechanical energy. Okay, and then be careful when you calculate the gravitational potential energy, because the position is far away from the Earth. You can't use mgh. You have to use this formula while you set the reference at infinity, which makes the formula like this. Okay, otherwise, as we discussed in class, the formula won't be like this. Okay, so reference set at infinity, then we can use this formula. Okay.